Hey guys, in this session we're going to be looking at excellence questions from the 3 calculus standards. So off we go to the first question. So this is the algebra excellence question. They've said that by writing z in polar form, proof of positive values of n, that zn plus z minus n is always real if modulus of z equals 1. So what we want to start out with in this question is, first off, we're going to write z equals that it's a complex number, which means we can write it as x plus iy. Now, if we're going to write this in polar form, it would be r cis theta. Now, one of the clues they actually give you is that the modulus is equal to 1, which means r, in this case, equals to 1. So then what we can say is z is actually equal to cis theta, because r is equal to 1. So once we establish that, now we can actually go about with the proof, because in the question is asking you that if zn plus z to the power of negative n, prove that it's always real. So I'm going to write down z to the power of n plus z to the power of minus n. Now, since z equals cis theta, I can write this as cis theta, let's put a line there, to the power of n plus cis theta to the power of negative n. Now, once again, remember that r is 1. I'm just not putting it in there. So according to De Moivre's theorem, we could write this as 1 to the power of n would be just 1. And then this would become cis n theta plus cis negative n theta. And then this is again 1 to the power of negative n. Well, that's just going to be 1 again. So that's why I'm not really fussed about the modulus, and I'm just looking at the argument. Now I need to prove that this is always going to be real. So what I'm going to do is I'm actually going to expand cis, and I'm going to write this as cos n theta plus sine n theta. Of course, this is getting multiplied by I, plus cos negative n theta plus sine negative n theta I. Okay, so, and I think this is where you kind of have to know something in trigonometry about odd and even functions. Now, if you had done trig, or even this is looking at, you might have done this in different integration. So one of the things is sine theta is an odd function. So in other words, if I do sine of negative theta, this would be the same thing as saying negative sine theta, because it's odd function. As for cos, if I have cos is actually an even function, so it's even an odd function. So if I have cos of negative theta, this is the same as cos theta. Now, if you don't believe me, just have a look at the cos graph. So let's say this is the cos graph right here, right? This is the cos graph. What happens is, because it's symmetrical on the y-axis, like it actually looks like this. So any value of cos of negative value is going to be the same as cos of positive, that angle. So whatever, if I take that's negative x, that's positive x. So you can see that cos of negative x is the same as cos of positive x. So this is something you need to know, because that's what we're going to do here. So I'm not going to touch cos n theta, the first one. I'm just going to leave it as it is. So that's going to be cos n theta plus I sine n theta. But now, because I've got cos negative n theta, and I can go to here and see that cos negative theta equals just cos theta. So what I could do is I could rewrite this as, instead of cos negative n theta, I can write this as cos n theta. And then plus, now looking at sine negative n theta, that can be replaced with, so if it's sine negative theta, it could be replaced with negative sine theta. So this would be replaced as negative sine n theta and of course there is an I in front. Okay, so once we do this, what you'll notice is your I sine n theta, which is this, and negative I sine n theta are going to cancel out each other, and you're left over with just cos n theta and another cos n theta. So this is going to equal 2 cos n theta. And I think at this point you can actually stop, because there is actually no i's in this equation. Therefore, it is always real. Because remember, for you to have always real, you need to have 0, 0i. And in this case, you have no i's involved in it, so this number must be real. Cool, that's it for this question. We've got a differentiation next. All right, guys. So in this question, you've got a cylinder that's going to fit inside this circle, and you're trying to figure out what's the radius that'll maximize the volume of the cylinder. So a couple of things to note first is that the circle's equation here is x squared plus y squared equals 10 squared. That's the first thing you need to notice. So the second thing is trying to write the equation, write one of the terms in the other one. So in other words, if I look at the volume of the cylinder is pi r squared h. So I need to get either h in terms of r or r in terms of h. Now I'm going to do the one with h in terms of r. So if you guys have a look here, so r is radius, which is from here to here for the cylinder. So that could be written as x. Okay, so that kind of nicely makes sense. Now if I take this particular point here, this is going to be xy, which means the distance from here to here is going to be y. So in other words, if I look at the relationship between y and h, I can see that y is equal to h divided by 2, because the height of the cylinder goes on both ends. So it's y from there to there, and then another y from there to there. So that's why h is equal to 2y, or y is equal to h over 2. Okay, so once we get that, we can also see that x is the same distance as r. So I could actually write, instead of x squared plus y squared equals 10 squared, I could write this as r squared plus y is equal to h over 2 squared equals 100. And I think this is what's going to help you rearrange one letter, which you could potentially use to substitute into this equation. Now, as I said, I'm going to use, well, you could actually use r squared, because look at this. I was going to do originally h in terms of r, but because you've got an r squared here and you've got an r squared here, so what I could do is I could write this as r squared equals 100 minus h squared over, well, h over 2 squared. So once I have that, now I could write the volume function. So volume is equal to pi r squared h. But because I actually showed you guys that r squared equals this, I could write this as volume is equal to pi multiplied by 100 minus h over 2 squared. That was r squared, and then multiplied by another h. So I could write this as pi times 100 minus h squared over 4 multiplied by another h. And of course, expanding all of this, I'm going to get a nice simple equation, which is 100 pi h minus pi h cubed over 4. So this is my function, this is my equation for the volume of the cylinder in terms of h. So now it's just the basic differentiate, equal to 0, and solve. So what I'm going to do is, if I have volume is that, then volume dash, which is the differentiation of volume, actually I might actually just put it as dVdh. So dVdh would equal 100 pi minus 3 over 4 pi h squared. Okay, and because the maximum occurs when the gradient equals to 0, so I can put 0 equals 100 pi minus 3/4 pi h squared. Rearranging this, I'm going to get 3 over 4 pi h squared is equal to 100 pi. And then carrying on this side, what do I got? My 3 pi h squared equals 400 pi. And now the pi's well, they kind of disappear. What I have is 3h squared equals 400. So h squared equals 400 over 3, which means the height equals 20 over square root of 3, whatever that value is. Now, just going back to the question, if you look at it, the question actually says, find the value of R that maximizes the volume of the cylinder. What we found is the maximum height, what we found is the height that's going to give the maximum volume. So what we need to do though is we need to substitute it back into the equation to figure out what the radius is. And to do that, we are going to use this equation here, which is R squared equals 100 minus h squared over 4. So because we already have h squared just 2 lines above, we can write this as R squared equals 100 minus 400 over 3, and the whole thing divided by 4. Which, when simplified, it gives us R squared equals 66.67, which means R is equal to 8.16 centimeters. Okay, and that's how you get the radius that's going to maximize the volume of the cylinder in this question. So in terms of grades, this is one of the old 2012 papers. So this is what you must do to excellence, to get an excellence. And I'm guessing for achieved or merit, it's, differentiating it, I would say would give you an achieved, and merit is solving something. But unfortunately, I don't have this, like the old schedules were different, so I can't really tell what they would classify merit as. Cool, that's it for this question, and we go on to integration next. Now this is actually looking at 2015 integration question from, I think it was question 1E. Now it was a weird thing because they actually gave you what you needed to do for this question, and they expected you to work out the volume. So the first bit of information they gave you in this question was consider the curve defined by the function y equals fx bounded by x equals a and b. So this is something you guys should have done before, because this is like looking at just definite integrals and then finding area underneath the curve. That's the first part of this question. The second part of the question goes on to say, like, if we rotate it about the x-axis, then you can actually figure out what the volume is, and this is the function to figure out the volume. Now again, what they're trying to say is that you find that area under the curve, and then you almost rotate it that way and then back that way to create like kind of like a sideways flower vase, almost, you can call it, or a pot. But yeah, so the only thing that you need to think about is you need to have a look at this particular equation. So to figure out the volume for this thing, this particular shape, is you have pi multiplied by b over a f of x squared dx. So this is the information they give you guys for that question. So the next part is the actual question itself. So here we go. They're saying that the graph below shows the function y equals cos x, and that's between 0 and pi over 2. So we've got 0 and pi over 2, which is just a cos curve. So this is just your regular cos curve, kind of doing its, that's just your normal cos curve right there. I can only draw half because I need that other space there. So they're asking you to find the volume created by this rotation. So if we go back to that equation, they actually gave, if you look at the previous slide, I'm sorry, I can't go back on this one, but it actually says volume is equal to pi, and it's from b to a f of x squared dx. I think that's what the equation was. So really, they've given you what you need to do. It's not that difficult, even though it might look complicated. So all we're really doing is to figure out the volume of this shape is we've got pi. Now we know what our b and a values are, which is pi over 2 and 0. And we have f of x squared, which is basically cos x squared dx. Now this could be replaced as pi over 2, 0. So basically, we're trying to find the integral of cos squared x dx between pi over 2 and 0. And that's it. So the important part is that I think in one of my videos I talked about in the integration series that there were two special cases. And one of the special cases was when you integrate cos squared x. You actually need to use a trig identity for this. And when you use the trig identity, it'll become a lot more easier to integrate, because right now this is not, you can't integrate this. So the identity that I was talking about was the double angle identity, which actually states that if you have cos of 2x, this could be written as 2 cos squared x minus 1. Now this was the identity itself. All right. So what we needed to do was we need to rearrange this identity to get 2 cos squared x equals cos 2x plus 1, and then cos squared x equals cos 2x plus 1 over 2. So this is the identity part. So now going from this part to here, we can write that the volume is equal to pi multiplied by the integral of pi between pi over 2 and 0. And instead of cos squared x, we're going to use this thing here, which will become cos 2x over 2 plus half dx. And I think from here, it should be pretty straightforward. And I'm going to work this on the next slide, folks. Okay, so from the previous slide, we had volume is equal to pi, and that was between pi over 2 and 0. And we had cos 2x over 2 plus 1 over 2 dx. So integrating this, we're going to get volume is equal to pi multiplied by integral of cos 2x would be sine 2x over 2, but it'll get multiplied by the differentiation of whatever's inside the bracket there, which is another 2 plus x over 2, and this is between pi over 2 and 0. So expanding this out, we're going to get volume is equal to pi multiplied by sine of 2 times pi over 2 over 4 plus pi over 2 over 2 minus, now sine of 2 times 0, that's going to be sine of 2 times 0 plus 0 over 2. I'm just running out of space. Okay, I've also got a 4 there. Now sine of 0 is 0, and so that whole right hand side bracket, I don't really need it. So what I'm left over with is pi bracket sine of pi over 4 plus pi over 4. Now sine of pi is equal to 0, so that means pi divided by 0 is going to be 0 as well. Pi sine pi. Whoa, sorry. We got sine of pi, which is this part, which is 0. That divided by 4 is going to end up being 0 as well. So what we have is pi times pi over 4, and my final answer, or the volume, is going to be pi squared over 4. So in terms of what you get for excellence and merit in this question, this is what you need to get for excellence. For merit, I think for merit it looks like correct interline, third line. 1, 2, 3. I'm not sure here, but looking at the schedule, it could be either here or here, but there's actually no achieved grade for this particular question. Okay, so that's it for this session, guys. Thank you for watching, and yeah, we'll just keep chugging along.